Hi, and welcome to the presentation of the paper Grain-128AEADv2, Strengthening the Initialization Against Key Reconstruction. My name is Martin Hell and I'm going to present this paper. This is a joint work together with Thomas Johansson, Alexander Maximov, Willi Meier and Hirotaka Yoshida. The outline of the presentation is as follows. I will start by giving an overview of the Grain-128AEAD algorithm and with focus on its initialization. Then I will give the key reconstruction attack that was presented by Chang and Turan. After that, I will give an analysis of alternative initialization approaches and then propose a general tweak to the initialization. This general tweak will be analyzed through conditional differentials, which will lead us to a definition of the Grain-128AEADv2 algorithm, and I will also then conclude the paper. Grain is a stream cipher that first appeared in the eCrypt eStream project, and the first version had an 80-bit key. Grain has been in the final portfolio of stream ciphers for the eStream project since 2008. Grain-128, which was a version with a 128-bit key, was proposed in 2006. This version should be considered broken since 2011. In 2011, another version with optional authentication was proposed, called Grain-128A. And most recently, Grain-128AEAD added mandatory authentication and supports for associated data. This algorithm is currently a finalist in the NIST lightweight cryptography standardization process. All ciphers in the Grain family of stream ciphers are based on a nonlinear feedback shift register, an NFSR, and a linear feedback shift register, an LFSR. On top of this, there is an output function that takes input from both the NFSR and the LFSR. For the versions that support authentication, there is also a register and an accumulator in order to hold the authentication tag. For details of how this authentication works, we refer to the design documents. The topic of this paper is the initialization procedure of Grain-128AEAD. So let us look a little bit more closely on that. What we do with the first part of the initialization is to put the 128-bit key and the 96-bit IV into the NFSR and LFSR respectively. Then we pad the LFSRs with 1s and finalize with a 0. Then, to initialize, for the first 256 time instances, we feed back the output of the stream cipher to the NFSR and the LFSR. Then, in clocks 256 to 383, we initialize the 64-bit register and the 64-bit accumulator. We do this while at the same time reintroducing the key into the LFSR. The idea to do this is to remove the possibility to clock the cipher backwards if the state of the NFSR and the LFSR are known. This key reintroduction is specific for Grain-128AEAD and was not present in the previous versions. Let us introduce some notations and some functions that we're going to use. By capital B, we mean the NFSR state at t greater than or equal to 0. By capital S, we mean the LFSR state at time t greater than or equal to 0. Capital A denotes the accumulator bits at time t is larger than or equals to 384, that is after the initialization process. And capital R is the content of the register at the same time, that is after the initialization of the cipher. Then we have three main functions to update the cipher state and to produce the output. ST plus 128 is the update of the linear feedback shift register. BT plus 128 is the update of the nonlinear feedback shift register, and YT is the output function. The details of the functions are not necessary for the rest of this paper, but the indices will play a somewhat important role. What we're going to do to simplify the notation is that we're going to group the bits that will be not interesting for us and leaving just the bits that will be interesting for us. So for the function that updates the LFSR, we denote this as st plus f prime, and then we group the other variables inside this function. And we do the same thing for the function that updates the NFSR and also for the output function. So to summarize the functions that we're going to use during our initialization, for the first 256 steps, we have st plus 128, which equals st plus our function f prime, which collects the other variables that we had in our feedback for the LFSR, plus yt, which is the feedback from the output of the cipher. We do the same thing for the NFSRs. We have st plus bt plus our function g prime, and then also here we add the feedback, which we denote yt. We do this in the first 256 steps in order to mix the key and the IV into the state. For the next 128 steps, we remove the feedback that we had from the cipher, but instead we reintroduce the key into the LFSR. And we do that while at the same time we initialize the registers A and R. And since these are 64-bit each, this initialization will be done during these 128 clocks. So after the initialization, we have in the LFSR the bits S384 up to S511. Similarly for the NFSR, we have the bit B384 up to B511. The accumulator will consist of the bits Y256 up to Y319, and the register will consist of Y320 up to Y383. In 2021, Chang and Turan proposed an efficient key reconstruction based on this initialization. The key reconstruction proceeds as follows. Assume that the state of the LFSR and the NFSR are known, and this can, for example, happen through a state recovery attack. If the state is known in any point in time, it is possible to clock the LFSR and the NFSR backwards so that we will reach the states that are present directly after the initialization. So we will have in a state recovery attack always the bits S384 up to S511, and similarly for NFSR, we will have the bits B384 up to B511. However, when we start clocking further backwards, we will start involving unknown bits. So looking at the equation for computing S511, this will involve the unknown bit S383 and also the key bit K127. Similarly, the NFSR bit B511 will include the LFSR bit S383 and also the NFSR bit B383. And the equation for Y381 will include the NFSR bit B383. The bits S511 and B511 will be known to us due to the assumed state recovery attack that we performed before. The Y bits will be found in our register and our accumulator used for authentication, and the bits Y256 and Y319, these can be immediately reconstructed from an authentication tag, while the bits Y320 up to Y383, they are not really known to us, but we need to guess these bits instead. And note that we do not need to guess Y382 and Y383, so we only need to guess 62 bits here in order to reconstruct all of these bits. So to conclude, Chang and Turan presented a key reconstruction from the known LFSR and NFSR state that requires 2 to the 62 guesses, that is guessing the bits Y320 up to Y381. If we in addition assume that these are known, that is the bits of the register are known, then no guesses are required and we can clock the cipher backwards and recover the key without any additional guesses. However, it is important to emphasize here that what we are doing here is that we are trying to break an already broken cipher. That is, we assume that the state recovery has been successful from the beginning, which in some sense would render the cipher broken anyway. The goal of this work is to design an improved initialization procedure, and we're going to take a very conservative approach. So our assumption would be that if we know the state of the LFSR and the NFSR immediately after the initialization, and in addition we also know the content of the register and the accumulator directly after the initialization, then it should still be infeasible to reconstruct the key. A first approach would be to investigate what happens if we push the key bits in some other way than just into the LFSR. So pushing the key bits into the NFSR instead would mean that we take the bit key 127 and move it from the update of the LFSR to the update of the NFSR instead. Looking at this equation system, we will see that we end up in a similar situation as before with an easily solvable equation system. So this is not a feasible approach. Another variant would be to push the key bits both into the NFSR and to the LFSR simultaneously. At first glance, this looks like a better solution because what we end up with will be a system of linearly dependent equations. Such a system cannot be as easily solved as in the previous cases, but if we generalize the equations to arbitrary times during the initializations, we can see that there is still a way forward for solving this equation. The algorithm to solve these systems of equations will start at t equals 383 and then we go backwards. So what we do is that we look at the first two equations, we can derive the value of bt and also the sum of st plus kt minus 256. After that we guess the value of st in order to determine kt minus 256. Then this guessed value of st can be verified later when we are computing bt minus 6. We elaborate more on this in the paper, and we also propose a more general recursive backtracking algorithm that is using the y values in order to verify the guesses that we made in previous steps. Another way of tweaking the initialization would be to make a parallel XOR of the key bits straight into the NFSR and LFSR. We have identified two problems with this. The first is that this will require more XOR gates and one multiplexer for each register cell, which will add to the hardware footprint of the cipher. A second problem is that the known Y values in the register A and R can now be used for verifying the guesses, and the parallel XOR into the NFSR and LFSR will give very much freedom for the attacker. This analysis leads us to a new approach for the initialization process. The idea is to remove the possibility to use the Y values in the registers A and R for verifying the guesses that we make. The solution to this is to separate the key introduction and the initialization of the A and R registers. We separate the initialization into three logical parts. In the first part, we use Cn clocks to initialize the LFSR and the NFSR by adding the pre-output bit as a feedback to these shift registers. In the next logical step, we use Ck clocks to reintroduce the key. And in order to keep Ck small, we are going to feed the first half of the key into the NFSR and the second half of the key into the LFSR. And since the key is 128 bits, this will give us 64 clocks. In the next and third logical step, we use Cm clocks to initialize the A and R registers. And since these are 64 bits each, the Cm will be fixed to 128 clocks. With Ck and Cm fixed to 64 and 128 clocks, if we want to keep 384 initialization clocks, this means that we will require Cn to be 192 clocks. This means that the key will be reintroduced at clockings 192 until 255, and the registers A and R will be initialized at 256 until clocking 383. Now, since the key will now be introduced earlier, a state recovery attack can continue clocking backwards in order to recover the state S256 and B256. But the last key bits that are introduced are now introduced through S383, where we introduce K127, and B383, where we introduce the key bit key 63. We can see in the equations here that we use Y255 in these equations, but since we have the known bits Y256 until Y283, these bits can now not be used for verifying our key guesses. Since our previous approach of recovering the key bits will now no longer work, we instead turn our attention to differentials. Differentials are interesting since we are assuming a state recovery attack and we can use known state bits in order to find these differentials. We're going to define a value that we call ZT plus 128 as bt plus 128 plus st plus 128 plus the functions g prime and f prime. If we expand this function, we can see that this will equal to 1 bit of the NFSR bt plus 2 key bits. If we initialize the cipher with a fixed key but 2 different IVs, we can now find the differential delta zt plus 128, which will be delta of the NFSR bit bt plus 2 key bits. But since the key is fixed, the differential here will be delta bt. And this will hold for all t larger than equal to 253. And the reason for this is that we know b256 and so on. And in the equation or in the function g prime, we have the lowest index bt plus 3. Now let us consider the conditional differential distributions d0 and d1, where d0 is delta bt, where the key bit kx is 0, and d1 is when we have the key bit kx equals to 1. If we have the case now that the two distributions d0 and d1 are not equal, we can find an empirical distribution d that can be used to recover kx using r samples, and the number of samples needed will depend on the distance between these two distributions, d0 and d1. And note that in this attack, this assumes that we now do 2 times r state recovery attacks. There are many such differentials to be explored, looking at different key bits and looking at different ways of having a delta IV. Here is one example with a reasonably high bias. If we have delta IV such that we change the IV bit 56 and then we look at the key bit K109, then if the key is 0 in this case, the bias that we have in delta B255 will be 2 to the minus 3.23, but if the key bit is 1, then we don't have a bias at all. Just outlining the attack here would be that we look at 2 to the 6.46 different samples. For each of these samples, we initialize the cipher with a random IV and determine this bit Z383. Then we flip the bit IV56, we reinitialize, and then we find Z383 again. Now we determine delta 383, which will be the same as delta B255 according to the previous analysis. And from the empirical distribution now, we can determine the key bit K109. It is clear here that this will leak information about one key bit, and it is also clear that we will require 2 to the 7.46 state recovery attacks, because for each sample we need to do 2 different state recovery attacks. We have more simulations with more biases in the paper, so we refer to that for more details. From this example, it is clear that using Cn equals 192 will leak key information under this type of attacks. Our goal now is to find the minimum value of Cn such that the cipher initialization is still secure under these types of attacks. So recall the differential delta zt plus 128. This will include bits from the NFSR and the LFSR, and the lowest index that we have is bt plus 3. So after a state recovery attack, we will have access to delta bt for the values t equals Cn plus Ck minus 3. And with Ck equals to 64 and a bias in delta bt, we will now require Cn to be larger than or equal to t minus 60. In a paper by Ma et al., they looked at differential attacks on the related cipher Grain-128A, and they found a distinguisher for 195 initialization rounds. If we use a rough approximation here, we can assume that there is a conditional differential in delta B195 plus 95 in this case, which equals to delta B290. Assuming this means that we will need Cn to be larger than or equal to 230. Let us now combine this analysis with a guess and determine attack. So if we come to the conclusion that we need Cn equals to 230, assume now that we can find a key leakage in Cn equals 229. So a natural choice here would be to pick Cn equals 256. So let us assume that we take this choice. Now we can guess 54 key bits. This allows us to reverse 27 steps and recover the states at B293 and S293. This now means that we can get said 290 plus 128, which would be delta 290. Now, if the key guess is correct here, we will get a bias distribution. Now, let us give a simple hypothetical numerical example. Assume that under a certain choice of key, the probability of delta B290 0 is 0.5 times 1 plus epsilon, with epsilon equals 2 to the minus 10. Using results from hypothesis testing, this means that in order to distinguish this distribution, we need 54 times 2ln2 times 2 to the 20, which equals approximately 2 to the 26.2 samples. And since we need to find differentials, we need twice as many key streams. So we need 2 to the 27.2 key streams. Now also assume that we have a state recovery complexity of 2 to the e. This will give us a total complexity of 2 to the e times 2 to the 27.2 plus 2 to the 54 times 2 to the 27.2, where the first part here is the complexity for the state recovery attack and the second part is the complexity for the distinguisher. So in summary, we can say that if we can find reasonably high biases in the state differentials, it would be possible to make an attack also when we have Cn equals 256, when we are assuming that we can guess a certain number of key bits and verify these guesses. So the main conclusions that we have reached so far is that first, we want to separate the key introduction from the AR register initialization. And two, even if we have Cn equals 256, it seems questionable if we have a conservative approach due to the presence of differentials in the known state. So based on this analysis, we propose a new approach to the key reintroduction in the initialization of the cipher. So we want to take a conservative approach, and here we choose Cn equals 320. So for 320 clockings, we will feed back the output of the cipher to the NFSR and the LFSR. Then, for 64 clockings, half of the key will go into the NFSR and half of the key will go into the LFSR. And finally, we will use CM equals 128 clockings in order to initialize the register and accumulator, because these are 64 bits each. So to conclude our paper, based on the attack by Chang and Turan, we have investigated the key reintroduction in Grain-128AEAD. We have considered both the algebraic key reconstruction and statistical approaches based on differentials. And we are assuming that we have a state recovery attack that has already taken place in order for these attacks to be successful. We propose a new version with this initialization, and we denote this new version Grain-128AEAD version 2. In this initialization, we have 320 plus 64 plus 128, which equals 512 initialization steps instead of the 384 in the previous version of Grain-128AEAD. This amounts for an increase of 33% initialization clocks. The result of this is that the Chang and Turan attack will no longer be possible, and also variations of this attack will also not be possible due to the separation of the AR initialization and the key reintroduction. Still, previous security analysis of the cipher will still be valid. The end goal that we have here is now that it should be difficult to reconstruct the key even if the state and the AR register values are known. And this concludes the presentation. Thank you for listening.